What about elimination addition? Underline that. Now here, oh, good question, Diana. So I forgot. Now that everyone wrote down elimination addition, I'm going to erase it. The first step of the reaction here, all of this generates, so we're using our strong base, hydroxide. Now what we've done is, notice we've introduced a phenol hydroxyl group here, so that this is an acidic proton. So what actually ends up happening in the reaction is that we have more hydroxide around. So that's going to just simply deprotonate this here. So our product then, the reaction goes, say, one step too far if you really wanted the phenol. But because it's done in the reaction is done in the presence of strong base, you're going to generate this deprotonated species. So in order to get the actual phenol product that you want, then in the last step you add in acid to reprotonate. So this will generate the final protonated product. Two nitrates. Okay, so thanks for pointing that out, Dan. I forgot to mention that. So in the reaction, the first step, all of the additional elimination occurs here with the hydroxide. In this particular case, it's a strong nucleophile. But then because you introduced down here in the bottom middle, this acidic functional group of the phenol, that gets deprotonated by the base, even if you don't want it to, just because it's the way it is with the acid-base chemistry. But then you're going to just add acid in the last step here on the right to protonate. Okay, so now let's try elimination addition. And this one here, the observation is that you can take a benzene ring with a leaving group, like a chloro, and put a methyl group down here to keep track of things. You can use a strong base, something that's oftentimes used as NaNH2 in the presence of ammonia as a solvent, the Al meaning liquid, and then this one also with H3O plus at the end. And you actually end up with two products. Should have put this further to the left. I'll just put them above each other. One of them has the amine at the same places where the chloro group was, but the other one has the amine meta to the methyl group here. So I encourage you, if you have space on the page, to write them next to each other. It's probably easier to see. So here the challenge is you end up with two products. One where maybe this is going to act as a nucleophile and attack here would be in the same place as the chloro, just like a reaction above. But you have another product with the amino group at a different position. Number two is this reaction occurs when you do not have electron withdrawing groups on the benzene ring. So in our example above, the SNAR reaction, we needed to have these electron withdrawing groups at ortho or para or both. But this reaction occurs without those. We just have this methyl group here, which is actually electron donating. So we need to come up with a mechanism that explains how this works without electron withdrawing groups and how we get these two products in particular. So I'll scroll up here. And the way this is thought to work is that we have this really strong base, like amide, NH2 minus, this Na plus NH2 minus. This is a strong enough base to actually pull a proton off of the benzene ring. Make this bigger now. So this seems quite unfavorable, and it is. And notice we've taken that proton off of the benzene ring, so we haven't destroyed the aromaticity yet, but we have a lone pair of electrons here. the negative charge. And now this is an unusual intermediate, but there's evidence that supports this, is that now with this leaving group, we're actually going to kick out chloride. I'm sorry, this is a single arrow now. And form this species here where we now have a triple bond, actually. This is benzene with the triple bond, or benzyne as the intermediate. And now this is going to be quite highly unfavorable energetically. Now what we can do is have our amide attack this. And now it could attack on either side of this benzyne. So let's have an attack with the here. Move these electrons back over here. We've restored our regular aromatic system. We have NH2. And now we have a lone pair back on this carbon. So that carbon is then going to quickly take a proton off of our ammonia solvent. We had NH3. So we'll go down here. Forming this product. And now this product here would actually could have pulled this proton off here to form this to be NH minus, which is why we would add acid in the end. So we'll have some acid-based chemistry that we don't want happening, just like above. So now that explains the product where these two groups ended up being para, or the amino group was in the same place as the chloro. But now, a bunch of different colors. Let's have the amide instead attack on this side. Right? Move these electrons up onto this oxygen and back over here to the benzyne intermediate. So we could attack from either side. And that one, just use that arrow to highlight that, is going to now end up forming a new bond with the nitrogen here. Lone pair of electrons now on this carbon, and same idea as above. So we'll have ammonia, and now that I have a little bit, I drew the wrong product here, sorry. Just really want it to be para. It's over here. And now this one, we'd actually see that unwanted acid-base chemistry, just like above, a little more space here. So we could take this proton off. I'm going to go the other direction. There's more space. And this is why we would add the acid in the end. I'm going to put it down a little closer. So another case where there's this unwanted acid-base reaction at the end, but it's because you're working with such a strong base and you're introducing a somewhat acidic proton in the end. And the same thing would happen over here. I just did not squeeze it in here. So another new reaction. This is the elimination addition form, because we're eliminating the leaving group first. So we have our strong base. This is what both has a strong base and a strong nucleophile in this reaction. Amide is taking the proton off, generating this unstable intermediate, which then kicks out chloride, forming this benzyne intermediate. This is the first and only time we'll end up seeing this. And then this can explain why we end up with two different products. Because now the nucleophile could attack, say, to either side of the alkyne-like species, and that will give the two products. If it attacks where the purple arrow is, that's going to give us this meta disubstituted product. And then we have some acid-base chemistry at the end that has to happen. We're going to protonate this really strong base to regenerate the species on the bottom, and then there's this unwanted acid-based chemistry. So two nucleophilic aromatic substitution reactions. They seem a little different than all the other ones that we've been talking about because we're switching around nucleophiles and electrophiles.
One of two grades.
I want to show part of the one above. One of the, actually, I'll go back down if we didn't get all that. But notice for the SNAR reaction here on the top, we have electron withdrawing groups on the benzene ring. That's kind of a key that we might see the reaction undergo this mechanism. For the benzyne mechanism, we still have the good leaving group, but we do not have electron withdrawing groups. And we generally have a really strong base, like sodium and okay? So now I'll go back down to the bottom.
I took one of those.
So there's a classic example of evidence for this benzyne reaction using what's known as the Diels-Alder reaction. May I ask, for those who took the first semester in the first part of the summer, did you cover the Diels-Alder reaction or not? Okay, excellent, you did. Great. So I won't necessarily go through it here just for time, but okay, actually let's do it. So while we're at it here, there's great evidence for this mechanism. So evidence for the benzyne intermediate is because remember with the Diels-Alder reaction, you could have your diene and an alkyne, for example, and you'd end up forming something like this in our pericyclic reaction. So then benzyne, I'm going to flip the alkyne and the alkene around. If you carry out a reaction with something like with benzyne, and you react this with, say, this diene, so then we could have a similar sort of reaction happening. And actually what's observed is you see something like this form. Try not to laugh. This is going to be a struggle here. Oh, that's a really bad start. You do that one.
That's true.
Okay, that's looking okay.
No, again. Oh yeah, that's okay.
I hear someone making comments. Is that Dr. Lopez? Your microphone is on. Okay, so there's actually evidence for this Diels-Alder product. And so this was a great example of providing strong evidence for the benzyne intermediate. Now, it's a nice connection back to the Diels-Alder reaction as well. All right, so now, one says all right a lot when you're trying to summarize things. A lot of material. We go all the way back up 17 pages. We were thinking about what's aromatic. We define this up in the upper right here with Huckel's rule. We thought about the importance of aromaticity or the reactivity. Considered our 5 major reactions with electrophilic aromatic substitution. Saw how mechanistically they're very similar, which is helpful. We then considered directing effects, orthometa-para, why that is. We can explain that mechanistically as well, using resonance and inductive arguments. And so hopefully there's a lot of consistency there in how we're explaining why a group is a meta-director, why another one is an ortho-pair director, and so on. And then squeezed in here between 6 and 7 were a couple of additional reactions that just came out of nowhere. In particular, the reduction reaction is very useful, the two-step approach of introducing an acyl group and then getting rid of the carbonyl group. And number 2, then, introducing a carboxylic acid is very useful. And then finally, these two new nucleophilic aromatic substitution reactions. So an enormous amount of aromatic chemistry, but hopefully you can see the very common themes coming up in this.